G'day guys, welcome back to the third video on multi-stage events and applications of probability. In this lesson, we're going to be adding new tools to the toolbox. The fundamental counting principle is one of three very powerful techniques used in probability. In this video, we'll learn about the other two, ordered selections and unordered selections, also known as permutations and combinations, respectively. Consider 6 friends, Rachel, Ross, Joey, Monica, Chandler and Phoebe stand in a line for a group photo. In how many ways can they be arranged? Before we look at it, take a guess. How many ways do you think they can be arranged? Write down your guess. Don't be shy. If we draw 6 spaces representing the line in which they stand, we can determine how many possibilities are available for each space. There are 6 people, so 6 of them can go in the first position. Once that is full, there are only 5 people left to go in the second position, 4 who can go in the third, 3 who can go in the fourth, 2 in the 5th position, leaving 1 person to be able to go in the last position. Using the fundamental counting principle, the total number of ways in which these arrangements can happen will be obtained when you multiply those 6 numbers together. Putting that into our calculator, we see that there are 720 different possible arrangements. How close were you? Are you surprised? I think it's quite mind-boggling. This can also be written using factorial notation. X factorial, which is represented by X exclamation mark, is the product of all whole numbers from X to 1. For example, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So a formal definition of ordered arrangements, or permutations, is that when the order in which a selection is made is important, we have an arrangement or an ordered selection. This is also known as a permutation. The number of ways in which n different items can be arranged is n factorial, which is equal to n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, and continuing down until we multiply by 3, then by 2, then by 1. As well as arranging people or things in line, we use permutations to determine the number of ordered combinations. If we consider selecting a captain and a vice captain from a group of 15 people, say a rugby team, there will be 15 people who can be captain, leaving 14 people who can be vice captain. 15 multiplied by 14 gives us 210 different combinations of captain and vice captain. Let's say that these 15 people run a race, but 2 people are disqualified. How many ways can the podium be filled at the end of the race? With 2 disqualifications, there are 13 people who can take out gold, leaving 12 people who can take out silver, and 11 people who can take the bronze. 13 multiplied by 12 multiplied by 11 is 1,716 different combinations. When the order is important, we are looking for it to be perfect. P for perfection, P for permutations, hence the smoothing tool that we used from our toolbox to get perfection with our work. In the other side of the toolbox is the chisel of combinations. With the chisel, there will be no order. Everything is chaotically unordered. C for chisel, C for combinations, C for chaos. Well, chaos might be a bit strong, but it starts with a C. If we're just putting our group into pairs, order doesn't matter. It doesn't matter if you were the first one chosen or the second one chosen. Let's put our group of friends, 6 friends, into pairs, or into groups of 2. First of all, we have Ross paired with each of the other 5 people. We have Rachel paired with the other 5 people, Chandler, Monica, Joey and Phoebe. Let's look at all the pairs. What do you notice? You can see there are double ups. There's a pair of Ross and Rachel, but that's the same as Rachel and Ross because the order doesn't matter. If we cross out the doubles, we can see that we reduce the number of combinations possible. Formally, using the fundamental counting principle, we see that there are 6 ways to choose the first person and 5 ways to choose the second person. Because the 2 players in each pair can swap places, we need to divide by the number of ways that these people can arrange themselves. That is, we're going to divide by 2 times 1, or 2 factorial. That gives us 15 pairs, and we can verify that by counting here. We have 5 pairs here, plus 4 is 9, plus 3 is 12, plus another 2 is 14, plus 1 is 15, and Phoebe has been paired with everyone in the other groups. So that gives us 15 pairs. Let's think about the upcoming World Cup cricket team. Now, we'll forget for a moment that the selectors need to choose different numbers of batsmen and bowlers. Let's just pretend that they can choose any 11 from the squad of 15 that they have named. How many different teams of 11 can they create? Let's forget about the 12th man for now too. We know that there are 15 ways to be able to choose the first person, 14 ways to choose the second person, 13 for the third, so on and so forth, until we get down to the 11th person where there's still 5 people who we can select to choose that 11th person. But now we need to get rid of the double up combinations. That is, how can those 11 people organise themselves? Well, we know that they can organise themselves as 11 factorial different ways, 11 multiplied by 10, multiplied by, and so on and so forth down to 1. Now, if we enter that into our calculator, we will get the right answer. But we can also use our simplification techniques where we can cancel out the 11, cancel the 10, the 9, the 8, the 7, 6, and the 5, leaving us with 15 multiplied by 14 multiplied by 13 multiplied by 12, all over 4 times 3 times 2 times 1. Putting this into our calculator gives us the answer of 1,365 different combinations. That means that there are 1,365 different teams that selectors can field. Amazing. And of course, Lotto. Who has dreamt about how they would spend the millions they would win from Lotto? Who's made plans even though they haven't bought a ticket? Let's see what your chances would be. We know in Lotto that 6 balls are randomly selected from a barrel of balls numbered 1 to 45. How many different selections are possible? How many different ways can we choose that first ball? There are 45 balls and 6 positions. So the number of possible selections is 45 multiplied by 44, by 43, by 42, by 41, by 40. But then, order doesn't matter for Lotto, so we need to divide by 6 factorial to get rid of the groupings that are the same, leaving us with 8,145,060 different combinations. That means you have one chance in just over 8 million of getting the right numbers and becoming a millionaire. Random fact, before 1989, there were only 40 balls in Lotto. How many more chances did you have of winning before 1989? Work it out and we'll discuss it in class. In summary, when approaching these questions, there are 2 main different types of questions. The first is in the form of how many. In how many ways can something happen? The second is what is the probability that the thing will happen. If we're faced with the question of how many ways, we're looking for an answer which is usually greater than 1. If we're looking at what is the probability, we're looking at an answer that will be between 0 and 1, a percentage, decimal, or fraction. Let's look at a quick example. Poker is a card game in which a player is dealt a hand of 5 cards from a deck of 52 cards. How many different hands of 5 cards are possible? How many different hands of 5 hearts are possible. Hence, find the probability as a decimal to two significant figures of being dealt a hand of 5 hearts. Part A. How many different hands of 5 cards are possible? We need to consider how we can fill those 5 cards in our hands. So there's 52 that can go in our hands first, times 51, times 50, times 49, times 48. Then we need to remove the combinations that are the same. So we need to divide that by 5 times 4 times 3 times 2 times 1, which gives us 2,598,960 different hands of 5 cards. Part B, the number of different hands of 5 hearts. There are 13 hearts in a pack, so that means to get 5 hearts in our hand, we have 13 cards that can be dealt to us first, multiplied by 12, multiplied by 11, multiplied by 10, multiplied by 9. Again, removing the combinations, we need to divide that by 5 factorial so we get rid of any double ups. So dividing by 5 times 4 times 3 times 2 times 1 gives us 1,287 different combinations of 5 hearts. Hence, find the probability as a decimal correct to two significant figures of being dealt a hand of 5 hearts. The probability of 5 hearts we know is 1,287 over the total number of hands, which is 2,598,960. Putting this into our calculator, we get the decimal of 0.0004953. Writing this correct to two significant figures means that we ignore the zeros at the start. So the first significant figure will be 4. We're looking at 49 because we want two significant figures, but the 5 coming after the 9 makes that go up to 50, so our answer will be 0.00050 to two significant figures.